Hi, and welcome to our lesson 2.1. You can see we're going to spend a few days here talking about the shapes of distributions. We're going to discuss four roughly types of distributions. Today, two of them, the uniform distribution and a normal distribution. And we say discuss their shapes. We're thinking perhaps in some terms of something like this. Suppose I flipped a fair coin, say 10,000 times. I should get about the same number of heads as I would tails. And if I did flip 10,000 times, then I should have about half of that in each category. So roughly 5,000 here. You know, it wouldn't probably be exact because most things don't come out perfectly in the real world, but it'd be around 5,000 flips in each category. A uniform distribution is one where the number of values in each category is roughly the same. Number of values in each category is roughly the same. So if we wanted to talk about the shape, center, and spread of a uniform distribution, the shape is fairly easy to come up with. It looks kind of rectangular. It's not as easy to talk about a center and spread in a uniform distribution. The center of this doesn't really make a lot of sense. This is a bar graph with categories, not numbers. Instead of center and spread, we usually talk about the number of values in each category, and it would make sense to talk about the number of categories that there are, describe what they are. If I were going to write a summary sentence about a uniform distribution, I'd say something like, this distribution is roughly rectangular in shape. See, it's never going to be perfect, and I'm going to abbreviate here. Distribution is roughly rectangular. Or you might just use the word uniform here, since that's the technical name for it. This distribution is roughly rectangular with about n entries in each of m categories. So if we were asked to describe a uniform distribution, our description would be something like this, and of course we'd fill in n and m with the number of entries and the number of categories. I'd like to have you think about, now I've showed you one distribution that would be relatively uniform, and that is flipping a fair coin over a large number of times. I'd like you to think of a couple other situations that you might expect to be uniform, and I'd like you to begin with across the days of the week. So think about something that happens relatively the same number of times each day of the week. Then I'd like you to do the same thing with some distribution that you think might be relatively uniform over the range of digits from 0 through 9. Will you pause the video and see what you can come up with? But here's my thinking. Over the days of the week, I would assume that roughly the same number of babies would be born each day in any given hospital. I happen to say Covenant. Over the digits 1 through 9, this is kind of cheating because I looked in the book, and they said, and it makes sense, that if we were to look at the last digit of people's phone numbers, roughly the same number of zeros, ones, twos, etc., because it's the first three numbers that are the same. The last ones vary, so you would expect to have about the same number end in each of the digits 0 through 9. Now I'd like you to look at this from the other direction. Think of situations that you would expect to be not uniform. That is, over the months of the year, something that changes month by month is not the same every time. Then over the days in 1 month, over the digits 0 through 9, and finally over the days of the week. I'll get you maybe started here. Over the months of the year, The number of daylight hours is not uniform. That is, there are some months when it's higher, some when it's lower. Number of daylight hours, not uniform. And I want you to think about something over the days of the month, then over the digits, and over the days of the week. Okay, will you pause that video, please? Okay, here are my thinking. Over the days of the month, something that doesn't happen the same each, or doesn't number the same over all of those days, is the number of walk-in bank customers. You get way more walk-in bank customers around the first of the month because that's when Social Security hits, and also on Fridays because that's when most people cash their paychecks. So it wouldn't be uniform over all the days in the month. I had a harder time thinking about this one. A thing where you'd get a non-uniform distribution, that is, not every digit has the same chance of coming up. And then I thought, well, if the last number is equally likely to come up, you know, the first number is not if you're in a given region. If you know people that have landlines still in Clio, almost every one of those numbers is going to start with a 6. So that's not uniform. And then over the days of the week, if you consider Sunday through Saturday, the number of cars in the school parking lot is not uniform because there are 2 days when there will be very few cars. So all of those would be non-uniform distributions. The next distribution that we want to talk about is called the normal distribution, and I'm going to ask you to try and draw yourself. You may have heard this called the bell-shaped curve. Okay, I very rarely make a perfect one, and I didn't right there either. In a normal distribution, you can see that the majority of data is in the middle. In fact, we'll learn later that not only is this the mode of the data distribution, it's also the mean and the median. You can see that things get low, they tail off towards the low side here. On the other side, they tail off towards the high side. So we have a characteristic that is one peak in the middle. It tapers off in the low and the high direction. A perfectly drawn normal distribution will have one inflection point on each half. An inflection point is where curvature changed from curving down, see how this is curving down, to where this is curving up. So an inflection point on each side, and again, this is not drawn perfectly by any means, but right in there, okay? So it has 2 inflection points. It approaches the x-axis but never touches it in theory. Doesn't touch or cross. So it has an asymptote at the horizontal. Okay, doesn't touch or cross. As far as the spread goes in a normal curve, there has been extensive study of distributions that are shaped this way because there are so many of them. And ladies and gentlemen, what they've concluded is that around 68% of data values is contained in between those 2 inflection points. Then the rest of the data again spreads downward. The distance between the mode line, the center line, and the line that contains one of the inflection points, that is called a standard deviation. Standard deviation. And again, we'll learn more about this later, but with it happens almost always that roughly 98 or 99% of the data will be contained within 3 standard deviations from the mean or mode here. So a lot of times we break it up this way. 99% of the data in a normal distribution is within 3 standard deviations plus or minus of that center line. 68% of the data is within 1 standard deviation on each side. So that's a lot of information about the normal curve. Situations that produce normal distributions, almost anything that's measured. So if you think about almost anything that's measured, if you think about heights, weights, you will see that this pattern makes perfect sense because the majority of people are real close to some center, some average height, and then you get some that are way shorter than that, some that are way taller than that. Almost anything that can be measured can produce and will produce a normal distribution. It's one of the most important that we'll talk about this year. So what I'd love to have you do is take a look at this distribution, which is the average age for groups, it says, of 5 workers drawn at random from that WestVaco data. This is the round 2 of layoffs, and so they took 5 workers, found their average age, okay? And you can see that it does somewhat have a normal shape. It's certainly not perfect, and you wouldn't expect something that you're actually measuring to come out to perfection, okay? It doesn't very often. But the mean of this distribution is right about there, and as you think about that, if that's 45 and that's 50, we're at around 47 years old. A standard deviation is where the curvature, or happens at the place where the curvature changes from down to up, and in this one it's probably right in there somewhere. Again, this is my estimate. It's by no means anything other than an estimate. So I came out at about 51 over here and at about 43 on this side. If 47 is the middle, it takes 4 units to get to 51. And let's see, if that was 47 and 4 units would get us, so the standard deviation here is about 4 years. If I were going to write a summary sentence then of this normal distribution, what I'd say is this: the distribution is fairly normal. Or you could use, normal. You could use the term bell-shaped. So we've got shape, now center, with a mean of about 47 years. And a standard deviation, which is the spread measure, and a standard deviation of around 4 years. Some people would say this is centered around 47, give or take 4 years, give or take, okay? And that's a good way to describe it. That's the end of today's lesson. We're going to ask you to get out there and look at the U-Tri at your earliest convenience, and we will talk more about these distributions in school.